astrocyte is. An astrocyte is something we refer to as a glial cell. Say glial cell. Glial cells are supporting cells of the nervous system, both the central and peripheral. And what they do is they perform some function that aids the neurons. So basically you have two types of cells in the central nervous system and the peripheral. You have your neurons, which are what pick up action potentials and graded potentials and all that stuff. And then you also have glial cells, which are often sometimes called glia. Plural from the called glia. Okay? And astrocytes are just one type of glial cell that exists in the central nervous system. Okay? So in the last video what we did is we mentioned that one of the goals of the fasting state is really to maintain ATP levels. Okay? And let's assume for just a second that the brain really isn't running on glucose, right? Let's assume the neurons of the brain really aren't running on glucose. And this is a really good picture that's going to depict what happens. Okay? So if you have glucagon present or cortisol present, all those hormones that tend to promote beta oxidation, we have release of fatty acids into the blood from adipocytes, right? You can certainly go back and watch the video on that. We have a video on that in the beta oxidation playlist. And so there are enzymes like hormone-sensitive lipase, and whenever there are certain hormones that get released, some of them certainly are glucagon, cortisol, things like that, you can release some free fatty acids into the blood, and that's what this FA is denoting. This is a free fatty acid. And the free fatty acids can be uptaken from the blood into astrocytes. So this dark yellow right here, this cell, this is an astrocyte. And astrocytes like this are glial cells, and they're in direct contact with neurons. So this cell, this is purple, this cell right here, this is a neuron. This is a neuron, and astrocytes serve the neurons by giving them food. It gives them nourishment. Okay? So we mentioned that the liver was one of the organs, because hepatocytes are one of the types of cells that perform ketone body biosynthesis. And it turns out that astrocytes do it as well. So let's talk about one group of ketone body transfer into the neuron. Okay? One thing, and this is the most complex thing to do, is that the fatty acids can actually be uptaken from the blood into the astrocytes. You notice that the arrow right here, the fatty acid, is pointing directly into the astrocyte. Right? In other words, the fatty acids can be uptaken into the astrocyte, and then we have the physiology from there. If you need to see the physiology and the biochemical pathways, I recommend that you go back and watch the previous video. We go into that. But the fatty acids, recall, get activated by fatty acyl-CoA synthetase, right? And that's an enzyme that burns an ATP, and you end up getting a fatty acid ligated to coenzyme A, right? And you get a fatty acyl-CoA, right? That's the name, fatty acyl-CoA synthetase. And then that activated fatty acid can then go and react with a series of four enzymes, assuming it's saturated, which are fatty acyl-CoA dehydrogenase, enoyl-CoA hydratase, beta-hydroxyacyl-CoA dehydrogenase, and then violase. And that ultimately gets this guy, which is acetyl-CoA, right? And that's the ultimate goal. But what the astrocytes can do is they can actually convert the acetyl-CoA through a series of steps. Recall that you have another violase that converts to acetyl-CoA, and an HMG-CoA synthase is using HMG-CoA, so this would be HMG-CoA. Certainly go back and watch the previous video for the structure that's trying to abbreviate this. And then this can react with HMG-CoA lyase, and that's going to give you acetoacetate, right? Acetoacetate is one of our ketone bodies. And we also have other ketone bodies. The main one that we're going to use for fuel, or at least we're going to use to make fuel, would be acetoacetate, right? Beta-hydroxybutyrate. And recall that these are in equilibrium with each other, but the main one that we're going to be using for fuel is this guy right here, one with a circle, and that's acetoacetate. Right, so that's our ketone body. So actually what the astrocyte can do is it can synthesize acetoacetate and beta-hydroxybutyrate. And it can actually shunt the ketone bodies into the neuron. In this case, this is our neuron, right? It can shunt it into the afferent neuron, which is shown here, right? And so then the afferent neuron can use the ketone bodies to put into, or to make acetyl-CoA, right? And it shows that right here. It's taking a ketone body forming acetyl-CoA, right? So in other words, what it's doing is first it's taking, right? It's taking this acetoacetate and it's going to ligate it to coenzyme A. Remember, it takes acetyl-CoA out of the CCA cycle, right? You get out the succinate, right? You get out the succinate, and then you should get aceto-acetyl. You should get aceto-acetyl-CoA, right? And we saw that in the previous video, aceto-acetyl-CoA, and then we react that with thiolase, right? This is thiolase. Then we should get two acetyl-CoA, right? And the acetyl-CoA then can be shunted into the TCA cycle of the neuron. So let's briefly say what we just did again without doing structures, okay? We're taking free fatty acids from the blood and moving them into the astrocyte. Then the astrocyte can take the fatty acids, activate them with fatty acyl-CoA synthetase, run them through beta oxidation to make acetyl-CoA, right? Then the acetyl-CoA can go into ketone body biosynthesis to make ketone bodies. Then you follow the arrows from this guy right here, and the ketone bodies can then go from the astrocyte into the neuron. Right? In this case, it's the afferent neuron. The afferent neuron is just shown here, right? And they go over to the afferent neuron, and they can be converted, assuming they still have to take that to acetyl-CoA. Then you thiolize that to two acetyl-CoAs, and then those go and react with citrate synthase in the TCA cycle. Okay? So that's one process by which we can actually generate energy with a neuron using ketone bodies. We actually take free fatty acids from the blood, put them in astrocytes. The astrocyte makes the ketone body, and then, of course, you shove the ketone bodies into the neuron, and then it goes from there. Ketone body metabolism with acetyl-CoA, and then the TCA cycle. Now, I hope that makes sense. So what the astrocyte is doing is basically just supplying the neuron with food, right? Because if the neuron is not getting glucose from the astrocyte, it has to be getting ketone bodies. So in other words, When it's running on glucose, that would be more along the lines when you're in the fed state, when insulin's present. So insulin would facilitate the uptake of glucose by the astrocyte, right? And then it just feeds glucose, right? When you have times of glucagon, when you're in the fasting state, the astrocyte will uptake fatty acids, okay, due to the physiology we've seen. But another method that the astrocyte uses, it can actually not just uptake fatty acids, it can directly uptake ketone bodies. And then it can dump those ketone bodies into the neuron, and then the physiology is the same from there. So what is the function of the astrocyte? It is to feed the neuron. Neurons are not terribly good at feeding themselves. They require the astrocytes. They require the astrocytes to feed them. So you can sort of consider the astrocytes like the unsung heroes, right? Without the astrocytes, the neuron dies. And this is especially apparent during the fasting state. The neuron absolutely requires the astrocytes to feed its ketone bodies, either from the blood or by converting fatty acids into ketone bodies. So I hope this video gave you a little bit of knowledge about the astrocyte and a little bit more about ketone bodies. See you in the next video. Playlist on amino acid metabolism. What we're going to do in this video is we're going to look at carboxyl phosphate synthetase 1 and the urea cycle. These are two processes by which we activate ammonia and then excrete it in the form of urea. So we're going to look at that. We're also going to talk about the factors that would cause you to have more activity in the urea cycle versus less. Also, one thing that's really important to do, and I'll keep harping on this in this playlist, is we're going to produce a lot of metabolites like NADH, fumarate, alpha-ketoglutarate, things like that that we've seen in other areas. And I'm going to really challenge you to think about where you've seen these before, where they go in the cell, what function do they have, because this is the only thing that's going to really give you a big picture of what the cell is doing at any given time. Welcome back. This is the playlist on amino acid metabolism, and what we're going to do in this video is talk in great detail about a cycle known as the urea cycle. And one thing I want to do before we ever get into the cycle is talk about what we've seen so far, and probably what you've seen so far in your metabolic pathways that you've seen up to this point, which is probably glycolysis. You've seen some in the pentose phosphate pathway, the TCA cycle, beta oxidation. But you've seen sort of the end products of metabolism. And the end products of metabolism that you've seen up to this point, you've seen carbon dioxide as one end product. Another end product is water. But let's think about this also. Where have we seen loss of carbon dioxide? Well, number one, in the pentose phosphate pathway, we saw that in 6-phosphogluconate dehydrogenase, right? We saw it there. We've also seen it in pyruvate dehydrogenase. We've also seen it in two other enzymes in the TCA cycle, which were isocitrate dehydrogenase and alpha-ketoglutarate dehydrogenase, right? So those are reactions that produce CO2. We also have reactions that produce water. The main one we've seen at this point is phenolates. Right? In glycolysis, phenolates produce water. Okay? And there are many other reactions that do this. If you've seen the electron transport chain video, you've seen that. If you know anything about it. Also, cytochrome deoxidase produces water. So these are two of our end products of metabolism. But there's a third that we really only see when we're talking about metabolism of amino acids. And that is ammonia, or ammonia at physiological pH. Usually I'll call it ammonia because that's usually what they term it in textbooks. So we'll call it ammonia, although note that at physiological pH it is ammonium. Okay? And ammonia is the third main end product of metabolism. And by the way, these are basically waste products. Although water and ammonia, and to an extent carbon dioxide are used in some reactions, they're mainly just considered waste products. Okay? And there's several ways that we get ammonia. Number one, there's two reactions that we talked about in previous videos. One was the reaction of glutaminase, and that's the reaction that I had labeled in blue as A. That's the reaction where we take glutamine and we deaminate it to make glutamate, and of course in the process we generate glutamate dehydrogenase to get it to alpha-ketoglutarate and ammonia. Okay, so these are two ways that we get ammonia that we've seen up to this point. And by the way, both of these reactions are mitochondrial. So these reactions, two reactions A and B that I'm talking about, they both occur in the mitochondria. Okay? Now, there are various other reactions that we'll see throughout our journey in amino acid metabolism that also produce ammonia. So when we do amino acid metabolism, we're creating a lot of ammonia. And that's something to keep in mind. When we do amino acid degradation, we are producing ammonia. Okay? And one thing you should be aware of is that ammonia is, at least in large amounts, is not good for cells. In fact, it's toxic. It's especially toxic to brain cells, and certainly once your brain cells suffer. So your body has to have a way of dealing with excess ammonia, which is going to be prevalent under two conditions. By the way, some teachers or professors will have you learn things in terms of like fasting or fed state. What I like to do more often is instead look at like what we have in the blood, right? So let's say that we're in the fasting state. Okay, let's say that we're in starvation. In other words, let's say we haven't eaten in a while. Okay, let's say we haven't eaten in a while. Well, you can imagine several things. Number one, our stores of acetyl-CoA, ATP, NADH, all of those things that are present, after we eat, those things are going to be low. So we're going to have low acetyl-CoA, low NADH, low ATP. All those things are going to be low. And you can also imagine that we're going to have high ATP, high AMP, high inorganic phosphate, things like that. Things that are associated with low energy. Those are the things that are going to be high in the blood, or excuse me, high in the cells, excuse me. Now here's the question. If we are in the fasting state, if we are there, what are we going to get? Well, how are we going to get that energy? How are we going to get the ATP? How are we going to get the NADH? Because what you're assuming is whenever we are in the fasting state, you're assuming that blood glucose is low, right? We don't have high enough blood glucose to seriously run on glycolysis, right? So we're going to have to find some alternative energy source. And really there are two energy sources, and those are lipids and amino acids. So whenever you're fasting, for instance, if you don't eat, let's say you don't eat breakfast, you go throughout the day, and you don't eat anything, by the time you get to dinner time, you are seriously going to be running on lipids and amino acids. So basically, when you're not running on glucose, the percentage of energy that comes from amino acid metabolism is going to sharply rise, right? And as we said, when you're doing amino acid metabolism, you're producing a lot of ammonia, right? So you can imagine that if we're not supplying ourselves with glucose, in other words, our blood glucose is low, we're going to be shifting our metabolism to metabolize amino. Constantly run glycolysis. So the generation of your ATP and NADH and so forth, all of those things are going to shift towards lipid metabolism and amino acid metabolism. So we'll sort of think of those going together. Okay. So, like I said, ammonia in large amounts is toxic to cells. So we have to have a way to deal with it. We have to have a way to get rid of the ammonia. And the way we do it is through this cycle called the urea cycle. Now, what I have written here at the top, what I copy and paste here, this is the reaction of carbamoyl phosphate synthetase 1. Okay. Carbamoyl phosphate synthetase 1 is a mitochondrial enzyme. Okay. And what this enzyme is going to do is it's going to activate ammonia. Okay. Ammonia won't just leave by itself. Okay. You have to activate it. And actually, the way we're going to get rid of it is by excreting it as urea. That's the way we're going to get rid of it. Okay. And this process of activating ammonia is actually pretty energetically expensive. As you can see right here, here's one ATP. We're going to do it in a different color, we'll do it in blue. Here's one ATP that we're going to lose right here. And then here's the second one we're going to lose in the third step. Okay? So carbamoyl phosphate synthetase 1 is going to burn 2 ATPs just to activate ammonia. And that by itself, based on our design, should tell you how important it is to get rid of this stuff. If you've got excess, you have to get rid of it. So the first step, bicarbonate is going to attack the gamma phosphate of ATP, and that's going to expel ADP as your leaving group. And what that's going to do, as it says here, it's going to generate a carbonic phosphoric acid anhydride. Okay? And this particular carbon right here that I'm circling, this carbon is actually very electrophilic. Okay? So, and by the way, it's a carboxylic acid derivative, but it's still very electrophilic. It's got 3 oxygens on either side of it, which generates a huge partial positive charge of that carbon. So that, and by the way, you also have phosphate attached to it, which is a good leaving group. So ammonia will come and attack that carbon. And you'll get a nucleophilic acyl substitution of phosphate as your leaving group, and that's going to give you this molecule right here, which is carbamate. Although carbamate is not activated enough, so you have to activate it further with another ATP phosphate transfer. So this oxygen right here, find it in my mouth, this oxygen right here is going to make nucleophilic acyl substitution on the gamma phosphate of another ATP, with ADP as your leaving group, and that's going to give you carbamoyl phosphate. Okay? This process that I'm talking about, this is also mitochondrial. So just like glutamate dehydrogenase and glutaminase are mitochondrial, so too is carbamoyl phosphate synthetase 1. Okay? The mitochondrial enzyme, so the process of activating ammonia takes place in the mitochondria. Okay? And what we're going to find about the urea cycle is that the urea cycle is unique in the sense that it actually spans 2 cellular compartments. Number 1, it spans into the mitochondria. That's where the pathway begins and ends. But also, most of the cycle actually takes place in the cytosol. Okay? So let's talk about the cycle. And by the way, one thing I want you to do, like I said in the objectives, is we're going to generate a lot of things in amino acid metabolism that are not actually part of the main pathway. They're sort of just metabolites that come off here and there. And a lot of these metabolites have places here and there in the cell, whether it be in the cytosol or the mitochondria. And what I want you to do is I want you to think, where is this go in the cell? Where have I seen this before? Because knowing those kind of things is really going to help you out when you're trying to piece together the cell. Okay? We're actually going to run into one of those molecules in this pathway. Okay? So let's look at it. So The beginning of the pathway is when you start with ornithine. Okay, ornithine is a strange amino acid. It's not an amino acid that's found in proteins. In fact, if you were looking at the structure, it's actually one carbon, one methylene group short of lysine. So if you're drawing lysine, just shorten it by one methylene group. Okay, so that's ornithine. And ornithine is going to react with carboxyl phosphate. Okay, and the enzyme that does this is called ornithine transcarbamylase. Let me write that down. It's called ornithine transcarbamylase. Okay? Ornithine transcarbamylase, and that's what they denote as 1 here. Okay? And what this enzyme is going to do is it's essentially going to transfer this component right here. It's going to transfer this component that's circling onto ornithine. And that's going to give you citrulline. Okay? Now this process, this ornithine transcarbamylase, this process occurs in the mitochondria. And once you generate citrulline, citrulline will then leave. Okay? Citrulline will exit the mitochondrial matrix, and it will then go into the cytosol. So all this process down here, this is all cytosolic. Okay? So now citrulline is in the cytosol, and citrulline is going to act with another enzyme, and this enzyme is called argininosuccinate synthetase. Argininosuccinate synthetase. Okay? And the reason it's called a synthetase is because it's a condensation reaction that requires ATP. If you've seen my videos in the past, you would know the difference between synthases and synthetases. If you recall, synthetases they were condensation reactions that require a nucleoside triphosphate. In the case of argininosuccinate synthetase, this particular synthetase requires ATP as the nucleoside triphosphate. And this particular enzyme is going to go through a very special intermediate that's shown here. It's the citrulyl AMP intermediate. Okay. Citrulline, and it's going to transfer the AMP group or the adenylate group onto this carbon right here. So this carbon right here, that's the carbon onto which the adenylate group is transferred. Why do we do that? Well, the reason we do that is because we're activating citrulline. Okay? We're raising citrulline up in energy. That AMP group is not going to be on that molecular density. It's just the intermediate in the reaction. So we're activating citrulline so that we can ultimately transfer an aspartate molecule onto citrulline. So the first step of the mechanism is to transfer that adenylate group onto citrulline. The last half of the mechanism, which is labeled 2B near the bottom, is where we use an aspartate amino acid and we cleave off the adenylate and we generate argininosuccinate, thus the name argininosuccinate synthetase. So what have we seen so far? Well, when we did carboxyl phosphate synthetase 1, we burned 2 ATP. That's already actually expensive. But not only that, we had to burn a third one. So that third one is in the enzyme argininosuccinate synthetase. Okay, I hope that makes sense. Now what we're going to do is we're going to talk about the third enzyme. And the third enzyme is called argininosuccinate lyase. Argininosuccinate lyase. Another way you might also hear this enzyme referred to is argininosuccinase. And I'm also going to tell you this because it's really important. Oftentimes when you see an aspartate attached to something and the very next enzyme is a lyase, oftentimes what that means is you're going to cleave off a fumarate. Okay? So whenever you see aspartate come on and the very next enzyme is a lyase, that's a good hint that the next substrate that comes off, or I should say the product that comes off, is fumarate. That's a very common motif in enzymes and amino acid metabolism and biosynthesis. Now, argininosuccinate lyase is going to produce arginine. So not only are we degrading we're not degrading, but we're getting rid of ammonia, but we're also seeing the biosynthesis of our first amino acid, that's arginine. This is the first biosynthesis, even though technically we're in the amino acid metabolism playlist. And even in the context of an amino acid metabolism chapter, you are going to see some biosynthetic reactions. This is actually how you biosynthesize arginine, is using the urea cycle. Okay, now remember what I said. I wanted you to think about, we're going to generate some metabolites in these pathways, and you've seen them before, at least you should have seen them before in previous studies. And I want you to think what happens to them. Okay, so fumarate, give you a minute to pause the video, and I want you to see if you can figure out where you've seen that before. You'll have to have a go at it. And fumarate is something we saw in the TCA cycle, right? So what we can do with fumarate is we can put it into the TCA cycle, right? We can put it into the TCA cycle, okay? And then when we put it into the TCA cycle, what enzyme does it react with? Well, it reacts with fumarate hydratase. So once we react with fumarate hydratase, what do we get? On my mouse, when we react with fumarate hydratase, we're going to get L-malate, right? So L-malate looks like this. So through one reaction, we're going to get L-malate, right? And then, once we have L-malate, we're going to react that with what? With malate dehydrogenase, right? And in the process, we're going to use NAD, and we're going to get out what? NADH, right? And that's going to give us oxaloacetate, right? So what happened? Well, we ended up burning 3 ATPs just to get rid of one ammonia molecule, right? And that seems very energetically expensive, and it truly is. But because we generate these fumarate, and we can put that into the TCA cycle, where by the end of the cycle we get one NADH back, we take away just a little bit of that energy exhaustiveness, right? We take just a little bit of it away and reduce the amount of loss, right? But the fact that we're willing to waste so much energy to get rid of ammonia tells you exactly how important it really is. Okay, so this is our synthesis of arginine, okay? And in the very last step of the cycle, we're going to react with another enzyme. This is purple. This enzyme is called arginase. Arginase, but you get the point. Arginase is a hydrolase, and what it's going to do is it's going to hydrolyze off urea. So this right here, this molecule is urea. And urea, at least in humans, this is the way that we excrete ammonia. We can't just simply excrete ammonia. We have to first convert it to urea, and then our nephrons can deal with it and so forth. So that's the way we excrete it. In fact, urea is also excreted in sweat as well, through enteric sweat glands. So we get rid of it that way.